Let's do the extra practice problems for Chapter 2. Number 1, classify the following as an element, compound, heterogeneous mixture, or homogeneous mixture. A punch made from fruit juice and soda water. That would be a homogeneous mixture. B, ice cream with chunks of cookie dough in it. Woohoo! That would definitely be a heterogeneous mixture. So would Moose Tracks. Yeah, Moose Tracks ice cream. If you haven't tried that and you like chocolate, you got to try that. C, a sample of iron which cannot be broken down into simpler substances. That would be an element. D, the pure substance made when magnesium and chloride combine. That would be a compound because it is made up of two substances, pure substances. E, sulfur. That would be an element because it can't be broken down any further. F, tea. That would be, if it's mixed well, that would be a homogeneous mixture. G, a chocolate chip cookie would definitely be a heterogeneous mixture, and a chocolate chunk cookie would be even more fun. And that would be heterogeneous too. H, sodium nitrate, which can be broken down into sodium nitrate and oxygen. So that would be a compound because it's not elemental. It can be broken down into the elements, but it is one molecule, made up of one molecule, and therefore it is a compound. Number 2, a student does a chemical reaction with two chemicals. The total mass of the two chemicals is 17.0 grams. When she is done, she finds that the mass of all the chemicals she has collected is now 17.8 grams. Uh-oh. The teacher says the student obviously contaminated the experiment with something else. How does the teacher know this? Well, because if she started with 17 grams, then she should end with 17 grams, and that is because of the law of mass conservation. Matter is neither created nor destroyed, it can only change form, and therefore she should not have come up with extra mass. And so what is the mass of the contaminants? 0.8 grams, because that is the difference. She started out with 17.0, ended up with 17.8, so 0.8 grams is the mass of the contaminants because she started with 17. Number 3, if any of you are thinking on number 2 that there could have been oxygen added, that could have been, but that's not the question he's asking for, so try not to overthink the problem. Later you'll come up with things like oxygen being added from the atmosphere, but not here. So if you're thinking that, just let it go. Let's not do that yet. Number 3, a chemist combines 63.55 grams of copper with 100 grams of chlorine gas. The result is 134.45 grams of a light blue powder and some leftover chlorine. How much copper and chlorine are needed to make 500 grams of light blue powder with no leftovers? Okay, so the first, we got to find the recipe. And so we have, the chemist combines 6355 grams of copper with 100 grams of chlorine gas. The result is 134.45 grams of, let's call it blue, because it's a light blue powder, isn't it? So we're just going to call it blue. Now, this gives us 163.55 grams. So we know that 163.55 grams is the total mass minus the blue powder that we made. So that will give us our leftover. So that gives me 29.10 grams, and that's going to be out to the hundredths place because both of these are to the hundredths place. That's the least precise. We're adding or subtracting, so that's what we're left with. So that's our leftovers. So what does that mean? Well, we're told here that we have leftover chlorine. So we know we used all but 29.10 grams of chlorine. So I'm going to go 100.00 grams of chlorine gas minus what was left over and unused. That will tell me how much of the chlorine was used, which is going to be 70.90 grams. That's how much chlorine was actually used. So we know that 63.55 grams of copper reacted with 70.90 grams of chlorine gas, And that produced 134.5 grams of blue substance. So far, so good. We were given this. We were able to figure out the leftovers from taking the total and subtracting the product. That gave us the leftovers. We know that there was leftover of chlorine, and so we took the 100 and subtracted the leftovers to find out how much actually reacted. This is what actually reacted. Okay, so that's our recipe. And so now we want to know how much copper and chlorine are needed to make 500 grams of the powder with no leftovers. Well, we know how to make 134.45 grams, so now we want to make 500 grams, so we're going to divide that by the recipe that we know, and that gives me I've got 4 significant figures here and 5 here, so I'm going to keep my significant figures, and so I'm going to get 4 significant figures. 7188, so I'm going to go 719. Okay, there is the number I have to multiply these by. So I'm going to multiply this by 3.719. I'm going to multiply this by 3.719. That's going to give me, in 4 significant figures, 236.3 grams of copper. In 4 significant figures, 263. I've got 7, so I'm going to go 7 grams of chlorine gas. And it actually comes out this time to 500, which is weird, because sometimes it won't come out just right. But that's how you figure out how to do A. B, another chemist combines 100 grams of copper with 111.57 grams of chlorine to make a solid. There are no leftovers. Is this the same compound as the light blue powder made in A? Okay, this was 63.55 grams of copper to 70. And this one is 100 grams of copper and 100. So if we take the ratio of copper to chlorine, let's just do it here and here. That'll tell us if it's the same thing. 63.55 divided by 49 equals. This one gives us, in 4 significant figures, 0.8963. This one gives me 0.8963. So are they the same? Yes, they absolutely are the same because they have the same ratio to one another. And that's how you'd figure it out, is you just see what the ratio is. This is copper per chlorine, and it's the same ratio, therefore they are the same. C, another chemist has 63 grams of copper and 35 grams of chlorine gas. There are no leftovers. Is this the same? All right, well, we just had here that this one, so this next one is 63.55 grams of copper to, I can tell you right now it's not the same. Because this is going to be above 1, isn't it? So I can look at that and tell you that's not going to be the same ratio. No, this ratio is above 1, like I said. This is 1.73. So no, the answer is no, that is not the same. If the compound made in A is composed of 1 copper atom to 2 chlorine atoms, how many chlorine atoms are in the compound made in C? If the compound made in A is composed of 1 to 2, this would be a 1 to 1. Okay, let's look at what he asked. If the compound made in A, which is here, 63 to 70, and he says this is 1 copper to 2 chlorines. So if you divide that by 2, what would you get? You'd get that number, wouldn't you? And this is the same number, but this number is half of this number. Therefore, this would be 1 copper to 1 chlorine, because this number is half of that. This is the same. So that was what he was asking for. Number 4, a chemist combines 30 grams of silicone with 32 grams of oxygen. The result is 60 grams of a solid with leftover silicone. How much silicone and oxygen should she use to make 150 grams of solid with no leftovers? All right, so first we have to find our recipe. So we have 30 grams of silicone, 4 significant figures, and 32 grams of oxygen, and the total that we make is 60.09 grams of product. And we know that if we add these two up, it's 62 grams. So that's going to give me, I'm subtracting this from this, and so I get 1.91 grams of leftovers. And we are told that the leftovers are silicone. So if we take the 30.00 grams of silicone and subtract the leftovers from it, it gives me 28.09 grams of silicone were used with every 32 grams of oxygen used. Okay, so this is our recipe right here. And that makes us 60.09 grams of product. Now we're told this time that we want to make 150 grams. So I'm going to go 150 grams divided by 60.09 grams, and that's going to give me what I have to multiply my recipe by. And I get, in 4 significant figures, because that's 5, that's 4, 2.496. Okay, so I'm going to multiply these, my recipe, by 2.496. Now remember, this isn't what I was just given because I had excess silicone, so I had to ditch the excess silicone to get my recipe, and then I multiply it by the number we came up with by dividing the 150 by what we already have. 4 significant figures. Okay, and if you add these up, they give you 159.98, which was about as close as we're going to get. Number 5 said the compound in number 4 is composed of 1 silicone atom and 2 oxygen atoms. If the chemist reacts 28.09 grams of silicone with 16 grams of oxygen to make a different compound with no leftovers, how many oxygen atoms are in that compound? Okay, so I'm going to erase this, and I'm just going to use this to look at because that's our actual recipe, isn't it? There's our recipe. And this time he wants to make a new compound, but he's using this amount of silicone. And he tells us here that with this amount of silicone, we have 1 silicone, and with this amount, we have 2 oxygens. So now we're going to do this with 16 grams of oxygen, which means we're going to have 1 silicone to 1 oxygen because it's half of that, isn't it? So that number is twice as much as this number. And if there's 2 oxygens here, that means there's got to be 1 there. So reacts with to make a different compound with little leftovers. How many oxygens? This time we have 1 oxygen, and that's why. See, this was held the same. So then that is twice as much as that number. 32 divided by 16, right, would be 2. So there's only 1 of them here. Number 6, a chemist is making 2 different compounds with the same 2 elements, nitrogen and oxygen. To make the first gas, she reacts 14.0 grams of nitrogen with 16 grams of oxygen and makes 30 grams of the first gas, which is composed of 1 nitrogen and 1 oxygen atom. Suppose she starts with 14 grams of nitrogen, but wants to make a gas composed of 1 atom of nitrogen and 3 atoms of oxygen. What mass of oxygen should she be using? Okay, well, we are given originally that it's 14.01 grams of nitrogen and 16.00 grams of oxygen. And we are told this makes 30 grams of gas. Okay, and this is composed of 1 nitrogen. Oh, I'm so sorry, that's nickel. 1 nitrogen and 1 oxygen. Some of you probably caught that. 1 nitrogen and 1 oxygen. And then it says, suppose she wants to make 14 grams of nitrogen but wants to use a gas that has 3 atoms of oxygen, what mass should she use? Well, it's going to be 16 times 3, which is going to be 48.00 grams of oxygen, because we want to use 3 of these, and this is one of these. We want to use 3, so we're just going to say 16 times 3. Yeah, I was right, 48. So what mass of oxygen should she use with no leftovers? It would be 48, 3 times that amount, because now we want 1 nitrogen to 3 oxygens, and that gives us our ratio 1 to 1. Number 7, which of the following atoms would be isotopes? You're looking for who has the same number of protons but differing numbers of neutrons. And so A and B have the same number of protons but differing numbers of neutrons. But C and D have the same number of protons, but look over at the neutrons. They have the same number of neutrons also, so they're not isotopes of one another. So the isotopes would be A and B. And then it says, which of the 2 isotopes you found in 7 would be the lightest? Well, A is 11 protons plus 12 neutrons, so that's 23 for its mass number. B is 11 protons and 11 neutrons, that's 22 for its mass number. Therefore, B would be the lighter of the 2 isotopes. Okay, a lot of work here. Practice your problems a bunch. When you feel ready, pray hard, take your test, and then read the first half of the next chapter. Have a very blessed week.